Welcome back to Chem Coding. I'm your host, and today we are moving out of the syntax laboratory and into the real world. This is part 2 of our Python Dictionary mini-series. In part 1, we did the heavy lifting of learning how dictionaries work, creating them, accessing data, modifying them, looping through them, and even touching on those sleek dictionary comprehensions. Basically, we made friends with curly braces. But let's be honest, you didn't learn Python just to store a list of groceries, you're here for the chemistry. Today, we're going to use dictionaries to solve 3 actual chemistry problems. That's right, equilibrium constants, molar masses, and predicting ionic compound formulas automatically, so you never have to crisscross charges by hand again. Let's dive in. First up, equilibrium constants. Let's look at the classic Haber synthesis for making ammonia. The law of mass action for this reaction is expressed as Kc equals NH3 squared over N2 times H2 cubed. Instead of writing a messy, hard-coded equation, we can store the structure of the reaction in a dictionary. We'll use positive exponents for the numerator and negative ones for the denominator. We name the dictionary Kc terms, containing items NH3 2 numerator, N2 -1 denominator, H2 -3 denominator. Now, let's say we have our equilibrium concentrations in another dictionary, concentration, containing items NH3 0.80, N2 0.20, H2 0.10. Define a variable expression to express the law of mass action, and it is initialized. Expression equals 1. Now, to compute the Kc, we multiply expression by each concentration raised to its respective power. This can be done by just looping through the terms. For species, power in Kc terms items, expression times equals concentration species raised to power. The final expression for Kc gives a slightly messy float, 3200. If you wanted to look lab report ready, use an F string with scientific notation. To do that with, say, 3 decimal places, you use format specifier like this. The output is 3.200 E plus 3, as we intended. What's nice in this example is that the structure of the math is encoded in the dictionary. If you change the reaction to something else, you don't touch the math logic. You just update the dictionaries and the loop does the rest. It's set it and forget it for chemists. Dictionaries, chemistry's secret weapon. Next, let's compute the molar mass of a compound from its formula. This has been done in previous videos with other ways, but dictionary makes the approach much more systematic and polished. Let's keep it simple with molecules made of carbon, hydrogen, and oxygen. First, our database dictionary of atomic masses. And our formula dictionary, say ethanol, C2H6O. The molar mass equals sum of atomic mass times number of atoms. The most Pythonic way to do this is using a generator expression inside the sum function. It's basically a one-liner that says multiply every atomic mass by its count and add them all up. In this code, for element count, in formula.items is a generator expression that loops through each element in the formula dictionary. Sum consumes the generator expression, adding up all contributions to get the total molar mass. If that looks like wizardry, you can use a regular for loop too. Molar mass equals 0. For element count in formula.items, molar mass plus equals atomic mass of element times count. Want to handle nitrogen, sulfur, or some exotic element? Just add it to atomic mass dict. Want to compute hundreds of compounds? Just loop over a list of formula dicts. It scales beautifully. unlike my coffee intake. Now for something a bit more sophisticated, predicting chemical formulas of ionic compounds from charges. Example, if I give you Mg2+ ion and PO4- ion, you want to get Mg3PO4-2. To do this programmatically, we 1. Store ion charges in dictionaries, 2. Compute the least common multiple of the absolute charges, 3. Use that to determine the subscripts, 4. Format the formula correctly with parentheses for polyatomic ions. First, we need helper functions for the greatest common divisor, GCD, and the LCM. Function GCD is an implementation of the Euclidean algorithm, and LCM is computed from GCD. Quick digression. Why did I use /floor division and divide before multiplying? First, the difference between the regular or true division. Regular division, A divided by B, always gives a float, like 7 divided by 2 equals 3.5. But floor division, A/B, returns an integer if both operands are integers, or a float if one operand is a float. It rounds down the result to the nearest whole number toward negative infinity. Example, 7/2 equals 3, because 7 divided by 2 is 3.5, floored to 3. -7/2 equals -4, because -3.5 floored toward negative infinity is -4. 3/2.0 equals 1.0, because 1.5 floored to 1 and it's a float. We need whole numbers for subscripts, so / is perfect. Of course, we could have used regular division followed by typecasting, int of A divided by B, but use of a single / operator is more elegant. Multiplication order. By dividing P by the GCD first, we keep our intermediate integer stays small, making the calculation faster and much more memory efficient. It's just good practice. Now, back to the main topic. We define dicts of ions with charges. We also need a way to tell if an ion needs parentheses like OH in CaOH2. For this, we define a function isPolyatomic ion. If ion is cation and we have a polyatomic cation, NH4, then we want this function to return true. Otherwise, return false. Default value for the second argument of the function is false. This corresponds to anions. For monatomic anions like F and Cl, the function returns false. All other cases are polyatomic anions, so it returns true. Now, the main function to construct the chemical formula. The function predict formula accepts cation and anion. Cation and anion charges are values. Next, compute LCM of charges. To get subscripts for each charge, we divide LCM by the magnitude of charge. Now, let's format subscripts. If the cation is polyatomic and the subscript is greater than 1, use parentheses to enclose the ion. Otherwise, just put the subscript. If the subscript is equal to 1, it is omitted in the formula expression. In this line, I used Python conditional expression or ternary operator. The general syntax is value if true, if condition, else value if false. Formatting anion works likewise. Finally, concatenate strings for cation and anion. Let's test it with some combinations. To recap, Conceptually, dictionaries map symbols to charges. LCM of charges ensures charge neutrality. Subscripts come from dividing LCM by charge. Parentheses for polyatomic ions. This is a nice example of how chemical rules, charge neutrality, and polyatomic grouping can be encoded in Python, mostly using dictionaries and a little bit of number theory. Before we go, here's a quick bonus. What if you have a huge nested dictionary of element properties and only want the group 1 elements? Time to use dictionary comprehension to filter. Group 1 elements equals k:v for k, v in elementprops.items if v sub 2 subgroup equals 1. Output gives group 1 elements. And to get just the symbols list, print list of group 1 elements .keys. We get the list h, li. This is the exact logic you'd use to build a searchable periodic table app. In this video, we've used Python dictionaries to encode and compute equilibrium constants, calculate molar masses from elemental composition, predict formulas of ionic compounds using charges and LCM, and filter elements by group using dictionary comprehension. If you combine this with the basics from Part 1, you've got a solid toolbox for chemistry coding. Feel free to extend the examples, add more ions, more elements, more reactions. If you enjoyed turning chemistry into code, hit that like button. Try your own reaction or favorite compound as practice. Thanks for watching, and I'll see you next time with more chemistry plus Python mashups. And remember, dictionaries aren't just for words, they're for science too.